Imagine a person running down the road. At any given time, we would know where they are and how fast they are going. But what if instead of that person, it was an electron? Well, not that simple. Enter Heisenberg's uncertainty principle. This principle tells us that the uncertainty in position multiplied by the uncertainty in momentum is greater than or equal to a constant. Essentially, the more precisely we know the position of an electron, the less precisely we can know its momentum and vice versa. So, to understand why, let's explore how matter behaves, both like particles and like waves. In quantum theory, a particle's exact location is described probabilistically. Instead of specific positions, we use a wave function to define where a particle may be found in space and time. Imagine the electron being 100% here and 0% everywhere else. On the other hand, waves, like ripples in water, are disturbances in a medium or through space, with properties like wavelengths, which is the distance between two crests or throws. And guess what? Momentum is linked to wavelength, wherein higher momentum means shorter wavelength and vice versa. But here's the twist. While a particle's position can be precisely defined, it lacks a wavelength, making its momentum uncertain. And while we know of its momentum through its wavelength, since it's spread out, we're uncertain of its position. So how do we make sense of these contradicting behaviors? That's where wave packets come in. Wave packets are like combining multiple waves, each with different wavelengths to localize the electron's position. The more waves we add, the smaller the possible positions become, but the more uncertain its momentum. Conversely, reducing the number of waves gives a more precise momentum, but spreads out the possible positions for the electron. And that's the uncertainty principle for you. So next time you're uncertain about something, remember that even electrons have their own uncertainties.